Hello and welcome back. This looks like a really long problem, but it's not that complicated. Let me explain what's happening here. I got these out. These are actual photo gates. And in this problem, there's a pendulum, a little ball tied to a string. It starts over here, 1.14 meters high, swings through the lowest point, and this photo gate records the velocity at the bottom. And then it swings through, it goes through another photo gate, and we know the velocity there at this point. So that's what's happening in this problem. It says we've got a 0.6 kilogram mass tied to a string, and it's pulled over to a height of 1.14 meters. Swings through here. The first thing we have to find is how fast is it going right here at the bottom. The second thing we have to find is if we know how fast it's going here, how high up is this photo gate? All right, so I'll move these out of the way and show you how to solve that. All right, the first part's nice and easy. This is, again, conservation of energy. All I do is I think what kind or kinds of energy does it have in the beginning, and then what kind or kinds of energy does it have at the end. All right, well, I would imagine if that pendulum were all the way over to the side and it started from rest, it doesn't have any kinetic energy. There's no spring energy because there's no spring in this problem. So the only other kind of energy it could have would be gravitational potential energy. So I'm going to plug in the gravitational potential energy initially. And then when it swings through the photo gate at the very bottom, the only kind of energy that it has is kinetic. So that's it. There's my formula. I got the gravitational potential energy that it starts out with is equal to the kinetic energy at the bottom. Rearrange my equation, and it turns out that the velocity is equal to the square root of 2 times g times the change in height. And I ended up with a velocity of 4.77 meters per second at the lowest point. All right, the second part of the problem is just a little bit trickier because when it's swinging through that second photo gate, it has two kinds of energy at the same time. It's a little bit higher than the lowest point, so that means it's got some gravitational potential energy, and it's simultaneously moving, which means it has kinetic energy. It has both of those at the same time. So my formula looks like this. I still say the total mechanical energy in the beginning is equal to the total mechanical energy final, and initially, all it had was gravitational potential energy, so know my formula for gravitational potential energy is mgh. Then, when it swings through that second photo gate, it's got kinetic energy and gravitational potential energy at the same time. So, plugged in my formula for the kinetic energy, plugged in my formula for the gravitational potential energy, and since I know the velocity, I know how much kinetic energy it would have at that point. So that's where the physics ends and the algebra begins. I plugged in all the numbers, I plugged in the height, plugged in the velocity, and I solved for the height of the second photo gate, and that comes out to be 0.75 meters per second. I think I forgot to show you the step where mass canceled. In all of these formulas, there's mass. So anytime I did this problem, no matter what the answer or what the mass was, I'd still get the exact same answer. So over here, I had mass and mass and mass. So we didn't even need to plug that in anywhere in any of these formulas. So the mass of the pendulum cancels out. There you go. That's how you use the conservation of energy to find the speed of a pendulum and the height when it goes through a photo gate. I'll see you in the next problem.